So I'd like to look at this in a more complicated situation, particularly in a not abelian situation of a quotient SL2 R mod SL2Z, and maybe the best analog would be the Selberg trace formula. I'm going to talk about a variation of the Selberg trace formula, which is the Kuznetsov formula. I didn't say trace formula. I said Kuznetsov formula. No, deliberately I just said. And also the title doesn't say trace formulae, it says spectral summation formulae. OK, so for those of you who have never seen the Kuznetsov formula, what does it do? So unlike the Poisson summation formula, it's not self-dual in the sense that both sides look roughly the same. On the one side, you have a sum over the spectrum, which is, in fact, in reality, a combined sum and integral. But that's not so important for the moment. And it's weighted by 2 Hecke eigenvalues. So you can fix your favorite integers n and m. If you don't like these weights, just put n and m to be 1. Then this is 1 and this is 1. And then you get rid of the weight if you want. Of course, this is an infinite sum. So somehow you have to make it convergent. So you weight this by an Archimedean test function. Let's call it simply mu pi. Mu pi is the infinite Langlands parameter, if you want. And then there is another weight that's an L function at the edge of the critical strip. And you take the residue of the Rankin-Selberg L function. So that's one side of the formula. And the other side is a more arithmetic side. It features Klosterman sums. So you take your 2 integers n and m, and you sum the Klosterman sum SNMC over all integers c. And then here you have some sort of integral transform of h nm over c squared. Now, as you all know, the Klosterman sum is given as follows. It's a sum over all coprime d modulo c. E is e to the 2 pi I, nd plus md bar over c. And if you want, you can view this, at least for n and m coprime to c, as the finite Mellin transform of the square of a Gauss sum. So if you take a normalized Gauss sum, tau chi normalized so that the absolute value is 1, and take the finite Mellin transform of that guy summed over all c, then you get this squared. And as you maybe know, a Gauss sum is kind of a gamma function. It's the p-adic version of a gamma function. And so this is a product of 2 gamma functions. And the Mellin transform of a product of 2 gamma functions is a Bessel function. So this Klosterman sum should be thought of as a finite analog of a Bessel function. And the Bessel functions are featured in this integral transform. So this h hat, you get this h hat by integrating h against the Bessel function. OK, so this is the formula. And as you see, so the 2 sides are very different. This is a purely spectral expression, and this is a kind of arithmetic expression. Historically, it's quite interesting. A precursor of this formula was given by Peterson, Hans Pettersson, for holomorphic modular forms on this side. And interestingly, Pettersson never stated this formula explicitly. What he did in 1932 is he computed the Fourier expansion of Poincaré series, which is basically all you need to describe this side. But at that time, there was no notion of Peterson inner product. So you wouldn't even know what an orthonormal basis is. This happened only in 1940. At that point, he introduced what is now called the Peterson inner product. And then you can spectrally expand everything, and then you get this formula. And then in this form, it was proved by Kuznetsov and independently Brüggemann in 1978. And there are various generalizations to other rank 1 groups, for instance, to SON1, also to SUN1. And this is in the early 90s. OK, so what can you do with this kind of formula? The nice thing about this formula is that you can read it in 2 ways. You can express spectral data in terms of arithmetic, and you can express Klosterman sums that come up everywhere in nature in terms of automorphic forms. The prime application, or so let's say that the first application, the motivation of all this is, so applications, is Linux, or Linux-Selberg, the Linux-Selberg problem. Namely, can you get cancellation in sums of Klosterman sums? Now, Weyls bound gives best possible bounds on an individual Klosterman sum, but if you sum Klosterman sums over the modulus without absolute values, you would hope you can do better, because there is cancellation in the sign. So this would be a result that algebraic geometry can never give you. The algebraic geometry can look at one C at a time. But if you sum over all of C, you hope to get some extra cancellation. And indeed, if you sum C of size x in a smooth way, SNMC, and I normalize it so that it has size roughly 1, then you do get square root cancellation. So this is bounded by x to the 1/2 plus epsilon. So there are x terms in this sum, each roughly of size 1, but the sign or the argument changes, and this gives you square root cancellation. And the implied constant depends on n and m. You can make this more precise. OK, next application is exceptional eigenvalues. So what's the smallest? Right. OK, yes. So here I'm using that I'm really in this situation. And we know that the Selberg eigenvalue conjecture holds for this group. If I replace this by gamma naught of n, and if I replace this with a condition of that kind, then I have to be more careful here, because then the exceptional eigenvalues enter. Right. OK, but in the simplest case, it's safe to say this. OK, yeah, so exceptional eigenvalues. What is the smallest eigenvalue of the Laplacian, of the hyperbolic Laplacian, the smallest non-trivial eigenvalue? And we would expect it's 1/4, so for such a congruent subgroup. We would expect it's 1/4, but up until now, this has not been proved, at least not for general congruent subgroups. And the first major step was Selberg's 3/16 theorem. That's a little smaller than 1/4, but much bigger than 0. And this was, in fact, proved in the 60s. So it was proved long before the Kuznetsov formula was established. But the proof is very similar in spirit. And nowadays, you can easily prove it in the same way using the Kuznetsov formula. OK, then most of the subconvexity results for L functions that I know depend in one way or another on the Kuznetsov formula. Primes in long arithmetic progressions. So if you want to count primes in long arithmetic progressions, on average, Bombieri-Vinogradov gives you basically up to, so level of distribution 1/2, But in certain situations, you can go a little bit above 1/2, and one of the ingredients is the Kuznetsov formula. You can do some funny applications that you wouldn't guess from a formula of this type. So we all believe that n squared plus 1 is prime infinitely often. We can't prove it. But an approximation would be to show that n squared plus 1 has infinitely often a large prime factor, a very large prime factor. And using the Kuznetsov formula, which doesn't seem the most natural tool in this situation, you can show that the largest prime factor of n squared plus 1 is greater than n to the 6/5 infinitely often. Now, whether you like this kind of result is up to your taste. But so what does this have to do with the Kuznetsov formula? Well, you start with a trick of Chebyshev to sort of detect the largest prime factor, and in the analysis, Klosterman sums come up. And in fact, sums of Klosterman sums come up. And once you see sums of Klosterman sums, the first thing you do is you apply this formula and then apply whatever you know about automorphic forms. This is the connection. So then sums of 3 squares, if you count solutions to n equals x squared plus y squared plus z squared, then you're counting points on the sphere, on an expanding sphere, and they equidistribute. And the equidistribution on of the solutions, one way to prove it is using a half integral weight version of the Kuznetsov formula. And finally, maybe, although this would require more space, but I squeeze it into here, you can use it as an approach to beyond endoscopy. So if you want to identify endoscopic limits, you're interested in identifying whether an L function has a pole at 1 or not. And it has a pole when the Dirichlet series, you can see this from the Dirichlet series, and if the coefficients are all big, then it somehow should, and if they don't oscillate, then somehow you should have a pole at s equals 1. And this is something you can potentially detect with such kind of formula. At least in certain situations. So again, this kind of formula may be a strong tool in such a situation. OK, so this Kuznetsov formula has been around for 30 years, and it's really one of the most powerful tools in analytic number theory. And again, the main point is you can use it in 2 directions. Whenever you see sums of Klosterman sums, you can apply it, but you can also apply it directly to spectral problems. And in fact, in many situations, you apply it back and forth. Of course, it's an involution, but if you do, say, Cauchy-Schwarz in between, then sort of you break the involution property, and you can use it back and forth several times. OK, so we have this tool. And we would like to generalize it even further. And can I write on this? Yeah. OK, so the next step would maybe be to look at this space, SL3R modulo SL3Z, and see if there is a similar formula available and see what sort of applications are possible with such a tool. OK, I can't move this. Well, anyway. Yeah, and indeed, there is such a formula, and it has pretty much the same shape. In fact, it has the same shape for every n, but so for SLNR modulo SLNZ. But let me focus on the case n equals 3. So again, we have a sum over the spectrum, which is really a combined sum and integral. So if you're pedantic, think of this as an integral, and then you have an appropriate measure here that is sometimes the counting measure and sometimes some other measure. Then you take a Hecke eigenvalue and another Hecke eigenvalue. In fact, you can have more refined versions. I'll talk about this later in a moment. You divide this by a weight, which is again the residue of a Rankin-Selberg L function. And you make the sum convergent by attaching a test function.
By the way, you didn't emphasize one point, which I view as the main achievement of Kuznetsov, and that's to invert that formula.
Right, right.
H hat first.
Right, right. So this was implicit in when I said that you can use it the other way. Of course, this implies that you have a way of putting your...
That Bruggemann did not do.
Yes, yes. So yes. So what you can do is you can pick your favorite test function here and have an integral transform on that side. And in fact, the transform, I mean, it's almost unitary. So you're almost integrating against the same kernel again. OK. Proving this, however, and this is probably what you wanted to point out, proving this is highly complicated. And
One of the most interesting things about it is there's a South African by the name of D.B. Sears, whose name I must bring in here, who was one of the unique students of Titchmarsh.
yes,
And Titchmarsh had missed the discrete square
Yes.
in this inversion.
Yeah. Right.
Kuznetsov.
right. But there is later there is a joint paper, Titchmarsh-Sears, and then they correct it. Yeah. Yeah. If it was Titchmarsh alone, then the inversion formula would have been easier. OK. Yeah, so you have to be a magician with Bessel functions to find this inversion formula and to prove it. And OK, I mean, by now, we kind of know how Bessel functions behave. I mean, in order to do all this, you have to understand these integral transforms. And this means you have to know something about Bessel functions. And OK, I mean, Bessel functions were studied in the 19th century. And OK, I mean, we pretty much know how they behave. There are some tricks and transitional ranges and so on. But more or less, we have all the relevant integral representations. We have the asymptotic formulas, even mostly uniform asymptotic formulas. So we have a reasonable understanding of Bessel functions. OK, let's see what the story is like in SL3. So here's the spectral side. It pretty much looks the same. And the arithmetic side also pretty much looks the same. So you get Klosterman sums. These Klosterman sums now have two moduli. So C is a pair of numbers. It's C1, C2. So you're summing over C1, C2. You have some sort of integral transform of little h that I now call capital H, which depends on n, m, and c in a specified way. They are not complete. I mean, they are coupled similarly as here. And here you have a finite sum over the Weil group. And the Klosterman sum depends on the Weil group, and the transform depends over the Weil group. The same happens here, except that the Weil group has two elements, and one of them is trivial. So it suffices to just write down the non-trivial element. Here, the Weil group has 6 elements. And one of the Klosterman sums that you encounter is if the order of the Weil element is 3, then you get what is typically called a hyper-Klosterman sum. Which looks like sum x, y, z equals n, m. So, well, anyway, x plus y plus z over c. However, this part is rather below the surface in this formula, and the critical term is really the long Weil element. Right. OK, but at the moment, we don't know how to do this. So, and for the long Weil element, these Klosterman sums are in principle understood, but they are rather complicated. So just to give you an example, if C1 and C2 are coprime, then this factor that factorizes into a product of two ordinary Klosterman sums. But in the extreme other case, so if you have something like NMPP, when they are highly non-coprime, have no cancellation at all. This is just on the nose P plus 1, at least if P doesn't divide NM. So this is essentially independent of N and M. It's just so on the diagonal, this is somewhat strangely. Now, the integral transform from little h to capital H is very, very complicated. And it was only very recently clarified by Jack-Buttkane. And he proved that the integral kernel is a Whittaker function. So that's the sort of GL3 analog of a Bessel function. So going from little h to capital H is now understood, but it's very complicated because we have a name for a Whittaker function, but we don't know how it behaves. I mean, it's a weird function with all sorts of funky things. And anyway, so in principle, we have an explicit formula. We don't know the inverse, although, so also Jack has some partial inverse, but the inverse problem is not really solved. That's true, yes. OK, so that's the shape of the formula. And what are possible applications? So I'll kind of go along this line and start with the Linux problem. There is cancellation in long Weil elements. So W is now the long Weil element. In long Weil element Klosterman sums, I divide by C1, C2 square roots. This is the expected size. So this has size 1. And if you sum C1, C2, say both of size x and smooth, then the trivial bound is x squared. But it's possible to show that this is bounded. So you get, this is not the perfect result. You would expect square root cancellation in both variables, but at least you can show square root cancellation in one variable. And that's a result of Jack-Buttkane. It's his thesis, in fact, from 2013.
Just to clarify there, since even at full level in GL3, everywhere around 5, we don't know.
Right.
We don't know the analog itself, so you're putting in the best bound there.
No. If I
you're putting some spectral.
Right. That's true. But if I remember correctly, the spectral gap would only show up if the two variables. I mean, I'm taking a simple case here. If the two variables are very, very unbalanced, then you see the spectral gap stronger.
I think Steve Miller proved that for the Laplacian,
Yes.
that it is true.
Yes.
Up to dimension 24, full level, everywhere around. So
OK. Now, I mean, one of the problems is that, I mean, ordinary Klosterman sums come up everywhere in nature. It's not so clear to me where these Klosterman sums, these funny guys here, where they come up in nature. I mean, is there a natural number theoretic problem where at some point these sums come up? I haven't seen one yet, which doesn't mean there is none. But anyway. OK, so the idea to prove this is you need an inversion formula, at least some kind of inversion formula to put your favorite test function here and then estimate the spectral side. OK, that's one application. Another application is density theorems. So that would correspond roughly to exceptional eigenvalues in Selberg's 3/16 bound. So Jacquet and Shalaika have shown sort of generic bounds how much the Ramanujan conjecture can be violated. And so typically the imaginary part, depending on your normalization, should be 0. And the imaginary part can be as bad as 1/2. At least we cannot prove much better. But you cannot improve this with the Kuznetsov formula. You can improve it slightly with other means, but not with the Kuznetsov formula. But what you can do is you can show that exceptional eigenvalues occur rarely. So if you sum over all representations such that the infinite component is, say, of height t and a ball of size O of 1, then this sum has two t² terms. That's the cardinality, basically, of this sum. But now you can put a weight that gets worse or that gets bigger the more the Ramanujan conjecture is violated. So you put here t to the imaginary part of mu j times 4. And you can prove this result, in fact. You can, well, right. So first of all, I don't think that this is more fancy than a trace formula, but that's a matter of taste. But it's okay. But let me say that the particular exponent is typically better with the Kuznetsov formula than with the trace formula. And besides that, I haven't seen this kind of result for GL3 being proved with the Selberg trace formula anyways. I'm sure something can be done along these lines, but I haven't seen it in print. And as Peter points out, for this particular kind of result, this formula seems to be a little stronger. So you okay, so the 4 is significant because it just recovers the 1/2 here. Because if you plug in something that's greater than 1/2, 4 times something that's greater than 1/2 is bigger than 2, so that's a contradiction. So you do recover the 1/2, but it says that very few forms can have, say, 1/3 here, right? Simply because you have such a big weight. And how do you prove it? You plug into the GL3 Kuznetsov formula a test function that is small on the usual spectrum and big on the exceptional spectrum. We only need an upper bound here. Yeah, so an upper bound is easy. I would not know how to do a lower bound, but luckily, I only need an upper bound. And then the weights, so proving that an L function is small is not so hard. Proving that an L function is big at s equals 1, that's a much harder problem. That I could not touch, but it's not needed here. OK, so this is a result of mine, also from 2013. Another application is on Sato-Tate laws, or on the Sato. So that's a kind of I don't know how you call it, vertical Sato-Tate maybe. So we fix P, fix a prime P, and we look at a Hecke eigenvalue at P. And we would like to study the distribution of this term as pi varies over the spectrum, say in a way that the Archimedean component is in a ball of size t. And so how do we study the distribution? Well, we pick our favorite test function. And Okay, here we need the weight, this residue of the Rankin-Selberg L function. And as t goes to infinity, this converges against the Sato-Tate distribution. So this is the Sato-Tate measure. And so f is a function that is, so f is, say, yes, okay, yeah. Yes, okay, fine. Yeah, so the measure does contain, okay, whatever. It is the measure that you would expect. Yeah. So f is a continuous function on the unit disk. So remember that these guys are now complex numbers. And on Ramanujan, they should be bounded by, I have to be careful. On Ramanujan, they are bounded by 3. So maybe I need like 3 times the unit disk or something. Yeah, in any case, this makes no assumption on the Ramanujan conjecture. So even if a few of these guys are exceptionally big, because the Ramanujan conjecture is violated, the theorem automatically implies that there can't be too many of them, because we still have this convergence. And even if a few of them sort of screw it up, there are not too many in order to destroy this theorem. How do you prove it? Well, idea of proof, it's very simple. By Stone-Weierstrass, you can write f as, or you can approximate f as z to the k times z bar to the L. If you can prove it for these functions, you can prove it for all functions. And then you just use combinatorics of Hecke eigenvalues in order to take kth powers and the bar of Lth powers. Then you can decompose it in a way such that you can use the Kuznetsov formula.
Is there a way to an Archimedean version of the exceptional eigenvalues using that technique?
Yes, you can make this p-adic. I just didn't state it now, but you have the exact p-adic analog of this, which is kind of this. I mean, it depends on whether you take the trace here or not. But yeah, you can do the same p-adically in Archimedes. So this is a theorem of myself and Jack Butkain and Nicole Raoulf from 2014, and was proved independently by Fan Zhu. Yes. Well, it's the most common thing is, I mean, I'm not so much interested in the operators here. I'm interested in the eigenvalues.
This you can prove using.
Yes.
But there's a stronger theorem. You projected a measure from.
Oh yes, that's true. Oh, and you want to have information on the.
Whether or not the limitation in your method in treating, you sort of focused on only one operator from this algebra of operators throughout. Is this a limitation of the method or just?
Oh no. So I'm taking here the trace because it looks nice, but I can do things. Say in this case. In the p-adic case, I can do things on the Satake parameters. Yeah.
So what is the statement of if you don't take the norm of mu? Like mu infinity has 2
parameters, right? But in this case, okay. In this case, okay. So let me be a bit more precise here. In this case, in fact, there is only one parameter, because an exceptional eigenvalue is necessarily on the wall of the Weil chamber, and you have unitarity. So an exceptional parameter is So how is it? So basically, it's something like.
The product of 3 numbers is 1.
And it's.
Why the 2 of them are complex functions? The one
Yeah.
real guy is the best.
Yeah. Yeah. And this is, by the way, okay, so to clarify, this is, by the way, the reason why you have only t squared here. I mean, the spectral measure generically is t to the 3. However, on the walls of the Weil chamber, the spectral measure drops. And the spectral measure is only of size t squared when you're in this situation. Okay, I have 20 minutes left, so I would like to come to the sort of most technical and maybe most advanced application of the Kuznetsov formula, and that's subconvexity. So here's the situation I'm interested in. I take pi on GL3, totally unramified, which just means it's a mass form for SL3 for the upper half plane modulo SL3Z.
Just to clarify that, so when you use a trace formula, you wouldn't have the weight there. You can probably remove. Do you know how to remove the weights in GL3?
No, I don't. I mean, on GL2 you can. Okay. Okay. No, I don't. Yeah, this weight is an artifact of the Kuznetsov formula. It's in the Kuznetsov formula. Okay, so I take pi unramified on GL3, and so it has an infinity parameter, mu1, mu2, mu3, such that the trace of this guy is 0. So basically you have two free parameters. And so let me project this down to the mu1, mu2 plane. So then mu3 is given in terms of, because the trace is 0. So then you have 6 Weil chambers in this two-dimensional space. So of course you can flip mu1 and mu2. That's flipping the first two coordinates. But then you can also flip these coordinates or these coordinates. And this gives you this and this. So these are the 6 Weil chambers, 1, 2, 3, 4, 5, 6. And I make one important assumption. I choose a parameter that's neither too close to the walls nor too close to the self-dual forms. If you're exactly on the coordinate axis, then one of the parameters is 0 and you're in a self-dual situation. So I choose two cones, two fixed cones. And I do this in each Weil chamber, but it's enough to do it in one. So I pick two cones, and they are fixed. I mean, I can take any angle delta here, and I can make delta as small as I wish, but fixed. And I allow my parameter to vary within these two cones in any of the Weil chambers. So then the analytic conductor of the associated L function, and let me call the norm T. Yeah? So if I'm sitting here, then all the mu's are roughly of size T, and also the differences of the mu's are roughly of size T. And the corresponding L function has conductor T to the 3, because the mu's are precisely the parameters that come up as gamma factors in the functional equation. Okay, so the convexity bound would be 3/4, and what we can prove, and that's a very recent result of Jack and myself, what we can prove is a subconvexity bound when you're on the critical line, 1/2 plus IT. I can bound this, so T is fixed. Think of T as being 0. By T to the 3/4, that would be trivial. And we can save a little bit. And here you see that I'm doing analytic number theory. So that's what we can save. In fact, we can save more if.
Sure that's safe?
Yes. So in fact, we could do something like this, but then the paper would be 20 pages longer. And we decided to sacrifice a bit of the exponent in order to reduce the length, which is already 50 or more pages. And OK. So formula is how it applies in practice. OK, we start as every analytic number theorist starts with an approximate functional equation. And what we do, so the idea is this is roughly equivalent, the statement, to a fourth moment asymptotic formula. So we sum over mu pi which is our favorite mu plus an O of 1 ball. That's t to the 3 terms. And let me focus on the 0.1 half. And we want an asymptotic formula for this in the form of a main term plus a power saving. If we can prove this, then we can prove this. By the way, let me say, why do we have to exclude? Oh, did I erase it? Probably I just erased it. Why do I have to be in these two Weil chambers? No, it's here. No, it's not. OK, whatever. OK, if I'm too close to the self-dual forms, the theorem is still correct, but trivial, because for the self-dual forms, the conductor is only t squared. If I'm too close to the walls of the Weil chamber, then the spectral measure drops. And first of all, I don't pick up many forms anyway. But then also, the whole proof becomes different because the spectral average is different. OK, so we want to prove this. And we prove it by using an approximate functional equation. And then we execute the spectral sum using Kuznetsov. By the way, Ivanets did precisely this in GL2 30 years ago. But in GL2, it's enough to estimate a second moment. Here, you have to do a fourth moment. Right. Well, he was shooting for the best possible exponent. He was shooting for a Weil saving. OK. So so what you get is roughly this. You save the square root of the spectral measure. I wouldn't have to take the eighth. So for a long sum, sixth moment would suffice because the spectral measure is t to the phi. That's right. But then I'm even overshooting because, let's see. OK, I see. OK. OK, potentially. Oh, sorry. OK, main term. That's what I mean. OK. OK. So it's a fourth moment, so I get 4 sums. N1, N2, M1, M2. They all run up to the square root of the conductor. Then I have, from the Kuznetsov formula, 2 C sums. And I have a Klosterman sum for the long Weil element N1, N2, M1, M2, C1, C2, divided by C1, C2, and a test function phi that combines the variables as N1, N2, C1 over C2 squared, and M1, M2, C2 over C1 squared. OK, first thing is we have to truncate the C sum. So we have to show, and this is a Whittaker transform of some nice function. And first thing is we have to show that for small argument, this function is small. That means for big C. If the C's are big, I want to truncate the sum. So if the arguments are small, I want to truncate the sum. OK, so we have to study this function. And indeed, we can truncate this roughly at height t. OK, next step. So this is, of course, this requires some work. This is by no means trivial. Next thing is we apply Poisson summation in all 4 variables. What do we expect? If the C's are of size t, And then we can hope that this has oscillation of size t. So the combined oscillation is of size t squared. The length is of size t to the 3/2. So that means that the dual variables are probably of size t to the half, 1/2. Because the combined oscillation here is t squared, and the length is t to the 1.5. So we would assume that the dual variables are roughly of size squared of t, which is great, because we have greatly reduced the length of these variables. This can be shown, but it's super hard. I mean, you have to imagine this is, so you get 4 integrals from Fourier transform, and then this phi is given, depending on how you write it, as a multiple integral over the spectrum of some function. So you have a 6- or 7-fold integral that you have to estimate. OK. But it turns out that this is at least morally OK. And then you have to compute the finite Fourier transform of this Klosterman sum. And here some miracle occurs, or at least something nice occurs. If you sum Sn1, n2, m1, m2, c1, c2 against an additive character, say e of n1 x1 plus n2 x2 over c1 plus m1 y1 plus m2 y2 over c2, then at least generically, you don't get something oscillating in x1, x2, y1, y2. These are the new dual variables. But you get a characteristic function. It's roughly, we are summing over everything. n1, n2 modulo c1, m1, m2 modulo c2. So it's a 4-fold, it's a complete sum. That's what you get from Poisson. It's a complete sum, and it's a 4-fold Fourier transform. And what you get is a characteristic function, and of course you have to normalize this properly. 1 over c1 squared, c2 squared. That's the number of terms you're summing over. x1, x2 is congruent to c2 modulo c1, and y1, y2 is congruent to c1 modulo c2. This is correct in generic cases. It can't be correct in general, because we have seen if c1 and c2 are both the same prime number, then there is no oscillation here. And for instance, if all the x's and y's are 0, you must get a big contribution. And this is indeed one of the new features in this situation. If you have an ordinary Klosterman sum, and you just sum it over everything, you can never have a situation where everything points in the same direction, even if the variables here are all 0, simply because the Klosterman sum oscillates. And if you sum over everything, you get 0. Here, it can happen in some configurations that everything points into the same direction simply because this guy is constant. I haven't really understood what's going on here, but this is just the case. The same happens for the Whittaker functions, by the way. If you look at the Whittaker function on the diagonal, it's bigger than usual. And this leads to a secondary main term. So you get a main term from the diagonal term, but you get a main term from here too. And this main term is quite hard to deal with. You need to find a 0 in the Mellin transform of the weight function in order to cancel a bit of the main term and make it manageable. So this is quite tricky to look at the contribution that comes from the diagonal here. This gives a secondary off-diagonal main term. OK, finally, after Poisson summation, you estimate everything trivially, which is a clever thing to do because you have nothing oscillating here anymore. So it's reasonable to just put in absolute values. But now you have to understand this function, so the Fourier transform of this function. And you would expect that each Fourier integral saves you a power square root of t. This is morally almost true, but the stationary phase procedure is brutal because you have like multidimensional stationary points. And already for the Bessel K, I mean, maybe you know this from the Bessel K function. So the baby case of a complicated stationary point analysis is the Bessel K function, kit of x times cosine hyperbolic pi t over 2. So that cancels the exponential decay. So this is x. Here is t. So this wobbles for a certain time. at square root size. So this is 1 over square root of t. And then just before it dies, it blows up for a moment. And this is because you have two stationary points that come together, and you get one degenerate stationary point at this point when x equals t. So you have a so the first derivative is 0, but the second derivative is 0 too. And you can imagine that in a multidimensional setting where you have a 4- or 6-fold integral, the weirdest things can happen because you can have all sorts of partly degenerate stationary points. Plus, this is all given by quadratic equations, which you can solve. But this is all given by cubic equations. And then if you solve a cubic equation and plug it into the next one and want to solve it, I mean, this is a disaster. So you can't do it. You can't do it by brute force. You have to be a bit more clever than just doing it by brute force. And what we actually do is, so somehow you have to estimate the regions where the first derivative is small. These are the bad points because there could be stationary points. And this is controlled by polynomials, which we have no control over, except that we know the degree. And luckily, so if you have a region that's given as an intersection of polynomials, it can't have too many connected components, because you can compute all the Betti numbers, and the number of connected components is in particular bounded by